Hello dear viewers. In this lecture series on spectroscopic methods, we have discussed many methods like NMR, UV visible spectroscopy, IR, fluorimetry and many others. Today in this last episode, we are going to discuss electron spin resonance, which is also called ESR. So before we start with the lecture, let us look at the lecture plan. In this episode, we will be discussing the basic introduction of the technique, the instrumentation, principle, its application and the comparison between the techniques NMR and ESR. So let us start with the introduction. ESR is also called electron magnetic resonance, that is EMR. Also it has one more name, that is electron paramagnetic resonance, EPR and ESR. So these three names ESR, EPR and EMR are the name of the same technique. In this technique, microwave frequency is absorbed by the paramagnetic substance. The paramagnetic substance is one which has unpaired electrons. It can be ion, a free radical, any compound containing unpaired electron and so on. This technique is used to establish reaction mechanism. It is also used to study the intermediates which are involved in various reactions. We can also study the extent of delocalization of the unpaired electrons, bond angles, relative energies of the unpaired electrons, the filled and unfilled molecular orbital in bonding scheme using this technique. Basically what happens, we have some magnetic energy levels, and when we apply a magnetic field, these magnetic energy levels, they split into two when unpaired electron is present, and this is the basis of ESR. This technique is very similar to the NMR. The only difference between the two techniques is the instrumentation and the application part. ESR is mainly concerned with the measurement of the energy which is required to reverse the spin of an unpaired electron. I have already said that the splitting of energy level takes place. So, electron with the same spin are in one level and electron with the other spin are in the other level. So, what happens when the energy is applied in the microwave region, the reverse of the spin takes place and electron, it goes to the higher level. So, this is the basic principle behind this. An electron behaves as a tiny magnet, same like a proton. A proton is also a tiny magnet. Similarly, electron is also a tiny magnet. This is because these both species, that is the electron and the proton, these are charged bodies, and any charged body which is in motion behaves as a tiny magnet. So here we are basically discussing the electron. So electron is a tiny magnet and it interacts with the external applied field. The magnetic moment produced by the electron is mu and it is proportional to the charge upon mass, that is we can say E upon m. The spin of the electron is either plus half or minus half. We all know that the electron exists in two spins, either it is moving clockwise or anti-clockwise. So it has two energy levels, one corresponding to the minus half spin and the other corresponding to the plus half spin. The magnetic moment of electron is 1000 times more than that of a proton, and the magnetic moment is given by the formula mu is the magnetic moment. This is equal to minus G beta S, where G is the spectroscopic splitting factor, which is also called gyromagnetic ratio. Beta is the magnetic dipole and it is measured in ergs per Gauss. And S, we all know, is the spin of the electron, which is equal to half. When electron is placed in an external magnetic field, the energy changes by a certain number of ergs, and this is given by energy is equal to mu h. Mu is equal to, we have already seen, minus G beta S into h, H is the strength of the external applied field. We can substitute the value of S, which is plus minus half into the same value G beta H. So, energy is equal to plus minus half G beta H. The electron which have the spin equal to plus half, they will point to the direction of the applied magnetic field, and they are going to decrease the energy by an amount of half G beta H. But the electron which have the opposite spin, that is minus half, they will point opposite to the direction of the magnetic field, and hence they are going to increase the energy by the same amount, that is half G beta H. So, the energy difference, that is delta H, it is equal to G beta H, and this is also equal to H nu, where H is the Planck's constant and nu is the frequency of the radiation. From this figure we can see this is the energy when no magnetic field is applied. So, we can see this is degenerate, all the levels are equal, but when we apply a magnetic field of strength H, this splits into two halves, or we can say two parts, not halves, it splits into two parts, the upper level and the lower level, and the difference between the two levels is equal to delta E, that is the energy difference, and it is given by G beta H or H nu. When the unpaired electrons in a sample are in thermodynamic equilibrium with the magnetic field, the population difference between the two energy level is given by the Boltzmann constant. So, we have N1 upon N2 is equal to exponent minus delta E upon KT, and delta E we already know is equal to minus G beta H. So, we have N1 upon N2 is equal to exponent minus G beta H upon KT, where K is the Boltzmann constant, T is the temperature in Kelvin, and N1 is the population in the upper level and N2 is the population in the lower level. So, from here we can see that the excess population in the lower level is present. There is an important term called resonance, which is usually used in NMR. What is resonance? When radiation of frequency nu, and remember this is the microwave region. So, when the radiation from microwave region of frequency nu is applied to a sample, then electrons in the lower level, they will absorb the energy and they will get excited to the higher level, and electrons in the higher level will emit the energy of the same frequency, and as a result they will return to the lower level. And due to large population in lower level, we can say that there will be a net absorption of energy, because more number of electrons are absorbing the energy than the number of electrons which are emitting. Hence, there is a net absorption of the energy, and this procedure is called resonance, or we can say when this procedure is going on, we can say that resonance is taking place. If there is a continuous absorption of energy, then what happen? Both the level will become equally occupied, and when both the level becomes equally occupied, this condition is called saturation, and in this condition no absorption occurs, and hence no resonance signal is observed in the spectra. So, we do not want saturation. So, to avoid this, we have another procedure which is called relaxation. Relaxation occurs to maintain steady state condition, by which the electrons that are being excited to the higher level, they lose their energy to the surroundings and they return to the lower level. So, what happens? There is higher population in the lower level, and this absorption and emission, it keeps on taking place, and a signal is observed because resonance is taking place. Coming on to the instrumentation part of ESR technique. In the instrumentation part, we can see we have a source. As in all techniques, there is a source of radiation. In this source radiates energy from the microwave region. So, generally we use klystron. Then this is connected to a resonant cavity cell containing sample. This is the resonant cavity cell, it contains sample. So, the radiation falls on the sample. We can see from this figure, it is surrounded by magnets all over, and then this cell is connected to the detector. Detector is further connected to amplifier, which is connected to the oscilloscope, recorder and computer. So, this is basically the schematic diagram of a spectrometer. There are various components of ESR. So, now we will discuss each component one by one. The first component is electromagnet. A very powerful electromagnet is used to generate a linear magnetic field. Modulation coils are present around the resonant cavity that are used to modulate the magnetic field. The second component is the source of microwave radiation. A klystron oscillator is usually used as a source and it normally operates at 9500 MHz and produces a monochromatic microwave radiation. The radiation is transmitted to the sample cavity by the means of waveguide. We have already seen this in the instrumentation, that is a schematic presentation of the instrument. The third part is the sample cavity, which is also called resonant cavity. This is placed between the poles of the electromagnet and the cavity is designed so that the sample can be irradiated in situ. In situ means inside the reaction medium. Next part is the solvent. The solvent plays a very important part. In every spectroscopic technique, we have seen that solvent has its own role. The ESR spectra can be obtained for gases, powders, crystals and frozen solutions. Solvents like toluene, glycerol, nuzol, triethanol amines are used to dissolve the sample. Solvents of high dielectric constant like water and alcohol should be avoided because they absorb in the microwave region. If we use solvents of high dielectric constant like water, what will happen? Along with the sample, the solvent will also absorb the microwave radiation. So, we won't get the proper result. Solutions of sample should be of 10 to the power minus 6 molar for structural determination and quantitative analysis. That is, we should use very dilute solutions. The next component is the crystal detectors. A silicon crystal detector is used which acts as a microwave rectifier. It converts microwave power into a direct current output. Phase sensitive detectors are used to reduce the noise level. Next we have auto amplifiers. After the detection of the signal, it undergoes a narrowband amplification which is done by auto amplifiers. Next we have recorder or oscilloscope. The signal from the detector is recorded and this recording is done with the help of oscilloscope or a pen recorder. So, this was all about the instrumentation. Now, we have G values. The G values is a measure of ratio between the frequency and the magnetic field. That is, it specifies the strength of interaction of a given electron with the applied magnetic field. We can in other words say that how strongly a electron, that is unpaired electron, it interacts with the applied magnetic field. This is measured by the G value, or we can say G value is the measure of the interaction of this unpaired electron with the applied magnetic field. The value of G is normally 2.00 for free electrons, but it is 2.00 plus minus 0.003 for all free radicals and ionic crystals. G value can be determined by noting applied field to achieve resonant absorption for a given microwave frequency. That means, we have to note that at which field the resonance takes place in the system. So, from there we can determine the G value. If the complex is a part of single crystal, then G is measured along different directions and it is used to deduce the symmetry of the complex. The G value confirms the distortion in the crystal. If we have the G value, we can easily tell how much distortion or what type of distortion is present in the crystal. As for example, we have hexa-aqua copper 2 positive ion. It is tetragonally distorted D4H. Its symmetry is tetragonally distorted D4H and it has two different G values. One in the direction parallel to the C4 axis and second in the direction perpendicular to the C4 axis. The isotropic and anisotropic G values. Anisotropic G values depend upon the orientation of the crystal. while the isotropic G values do not depend upon the orientation of the crystal. In anisotropic G values, the G value and the resonance frequencies vary according to the orientation and the external magnetic field, while in case of isotropic G value, the G value and the resonance frequency do not vary according to the orientation of the external magnetic field. The spectral line obtained when the spectra is recorded, it has 4 important properties: the intensity, the width, the position and the multiplate structure. So, these 4 properties are very important. From the intensity, we can tell what is the concentration of the unpaired electrons or the concentration of the free radical or paramagnetic substance, because intensity is proportional to its concentration. The width depends on the relaxation time of the spin state. That means relaxation time means how much time is required for the electron to come back from the higher level to lower level. So, from the width of the peak we can tell about the relaxation time. The position also tells about what the kind of substance is, and the multiplate structure basically tells about the interaction of the electron with the nucleus. So, this interaction of the electron with the nucleus is basically termed as hyperfine interaction. It is also called electron nucleus coupling. When an unpaired electron in a molecule is delocalized and it interacts with a nuclei, and this nuclei should not have 0 spin, that is, there should be some spin of the nuclei, then only the molecule cause further splitting of the electron resonance line, and this is called hyperfine coupling. The splitting of the individual resonance line into components line is referred to as the hyperfine splitting. We also have fine structure. The fine structure occurs in a crystal containing more than one unpaired electron spin, while the hyperfine structure, it arises when an unpaired electron gets closer to a nuclei. That is, hyperfine structure arises as a result of electron nucleus interaction, and it is a smaller effect than the fine structure. Electron nucleus coupling constant are much bigger than those of the nucleus interaction, and the reason behind this is, the first reason is, an electron can reach nucleus more closely than another nucleus. This is because electron is negatively charged while the nucleus is positively charged, and this electron and nucleus, they will interact due to the attraction, and electron can reach to nucleus closely. But in case of nucleus, both are negatively charged, so after a certain limit they cannot come closer. Therefore, this nucleus interaction is, we can say it is much less. The second reason is, the magnetic dipole of nucleus is approximately 1000 times than that of an electron. So, this is also a reason why electron nucleus coupling constant are much bigger than those of nucleus. Hyperfine interaction, the isotropic and anisotropic coupling constant. Electron spin resonance signal shows the presence of unpaired electron in a sample. That means, in ESR, if we are getting a signal, it means that we certainly have an unpaired electron. And the intensity of the band, it is proportional to the number of unpaired electrons. So, if we have an intense band, we can say more number of unpaired electrons are present, and if we have a less intense band, then the number of unpaired electrons present in the sample are less. The width and the shape, they gives information about the relaxation process in the sample. Relaxation process, once again I will repeat, it is the process when the electron from the higher level, it emits some quanta of energy and it returns to the lower level. So, the width and the shapes give information about the relaxation. The isotropic and anisotropic coupling constant. The hyperfine structure of a spectra gives information about the environment of the molecule and the distribution of the electrons in the molecule. And second information which we get from hyperfine structure is the identification of the paramagnetic substances. So, these two information are obtained from the hyperfine structure. The isotropic and anisotropic coupling constant, in this we have h nu, that is the energy difference delta E, it is equal to G beta h. We have already seen this formula. This formula we can write as G beta and h can be written as h naught plus h local, where h naught is the applied magnetic field and h local, it is the magnetic field due to nuclei. The effect of magnetic field of the nuclei on the ESI spectrum is known as hyperfine interaction, and it is responsible for the splitting of ESR line. And how? We will just see. So, looking at this figure, here we can see there is no applied field. So, there is no splitting, but when there is a field of H naught which is being applied to the system, then it splits into two levels, one having the minus half spin and the other having the plus half spin. In this case, there is no proton, only the splitting is due to the unpaired electron. But if we study the case of hydrogen atom, it has one proton and one electron. This electron is going to interact with the proton because the proton also have some spin, and which is equal to half. It can be again plus half, minus half. So, these two levels, again these will interact with the spin of the proton, that is the plus half spin and the minus half spin, and these two levels will further split into doublets. So, we now have 4 levels, and we can see the transition. There are 2 transitions. And if you look at this figure, the upper one, which where we have only one signal, this is due to the splitting of the electron magnetic lines when no proton is present. We have only one peak, but when a proton is present, then we have 2 signals. This is due to the interaction with the proton. We have another example. This is the example of a methyl radical. In methyl radical, we have one unpaired electron and we have 3 protons. So, this unpaired electron will interact with the 3 protons, and every time the splitting will increase. Here we can see there is no applied field, so no splitting takes place. In the second case here, this splitting is due to the applied magnetic field. The electron, the magnetic line split into 2 levels, the lower level and the upper level, one having the plus half spin and other having the minus half spin. Here no interaction of the electron with the proton takes place. Next we can see at this level, this electron interacts with the first proton, and both the lines they split into a doublet. This spin of the electron, it interacts with the plus half spin of the proton and with the minus half spin of the proton. Similarly, here also this positive spin of the electron interacts with the minus half of the spin of the proton and the plus half spin of the proton. Further, this reacts with the second proton. On interaction with the second proton, this single line splits into a doublet. We had 2 single lines in the upper level, so both of these splits into a doublet. Again, this plus half will interact with the plus half of the proton, and here with the minus half of the proton. Here also the minus half will interact with the plus half of the proton and the minus half of the proton. Next we have the third proton. When it interact with the third proton, what happens? It will again, each line will again split into a doublet. Similarly, as in the earlier case, this will interact with the positive half spin of the third proton and also with the negative half spin of the third proton. Similarly, each line will interact in the upper level also and in the lower level also. So, the spectrum has equally spaced 4 hyperfine lines, and the ratio is 1:3:3:1. So, how do we calculate the number of lines in a spectrum? There is a formula to calculate the number of lines in a spectrum, and the formula is 2I plus 1, where I is the spin of the nuclei. Example, we have N14. The spin of nitrogen is 1. So, we will have 3 line spectrum. Putting the value of N, putting the value of I in the formula 2I plus 1, we have 2 into 1 plus 1 equal to 3. So, we have 3 line spectrum. In case of manganese, whose spin is 5 by 2, it will have 6 line spectrum, because 2 into 5 by 2 plus 1 gives 6. For n equivalent nuclei, this was when the electron is interacting with one nuclei, but if the electron is interacting with a number of nuclei more than one, then we have the formula 2ni plus 1, where I is the same, the spin of the nuclei, but n is the number of nuclei, and in this case all the nuclei are equivalent. So, we have in case of N14, if we have 2 equivalent N14, a single electron is interacting with 2 equivalent N14, then spin is this spin is equal to 1. We have, according to the formula, we have 2 into 2, this 2 is the number of nuclei, into 1, 1 is the spin of the nuclei, plus 1. So, it gives 5. So, we have 5 line spectrum. For non-equivalent protons with different coupling constants, in this case what is happening? A single electron is interacting with more than one nuclei, but the coupling constant of both the nuclei are different. Suppose the coupling constant of first nuclei is A1 and that of second nuclei is A2, and A1 is greater than A2, then a doublet is caused due to the interaction of the electron with the first nuclei, and this doublet, it further splits into another doublet due to the interaction with the second nuclei. We also have a term called Kramer's degeneracy or zero field splitting. So, up till now we were studying the interaction of electron with the proton. But what will happen if there are more than one paramagnetic electron, that is more than one unpaired electron? The electron will interact with another electron also. So, in this case, if we have even number of electrons, suppose 2 electrons are present, the 2 electrons may be present on the same atom, or one electron each will be present on 2 atoms of a dimer. The degeneracy of the electron in such atoms is resolved by the internal magnetic field given by delta H of the electrons, even in the absence of magnetic field. That means, if we do not apply any external magnetic field, then also the degeneracy of the electron will be resolved because of the internal magnetic field, and this is called zero field splitting or fine splitting. And this spin degeneracy can also be resolved by crystal field. But for odd number of electrons, if we have 3 electrons or 5 electrons, any odd number, then what happens? Spin degeneracy of energy level remains doubly degenerate. It does not resolve, or it is not destroyed, and this is called Kramer's degeneracy, and it can only be removed by the application of external magnetic field. So, this was the difference between the Kramer's degeneracy and zero field splitting. Next topic is the spin Hamiltonian. The scheme of energy level can be represented in terms of Hamiltonian because ESR is concerned with electron and nuclear spin. So, it is called spin Hamiltonian and it is given by Hs. The spin Hamiltonian Hs has the formula, this is equal to G beta H S Z. We know what is G, we know what is beta, we know what is H. Sz here is the spin operator plus A Sz. A is the hyperfine coupling constant minus the third term which is Gn beta n H Iz. Gn is the G factor of nuclei, that is the gyromagnetic ratio of nuclei. Beta n is the magnetic moment of the nuclei, and H is the applied magnetic field, Iz is the nuclear spin operator. The first term is the energy of interaction of the magnetic moment of the odd electron with the field. The second term is the interaction between the moments of electron and the magnetic nucleus, and it is responsible for the nucleus hyperfine structure. The last term can be neglected and it shows the energy of the nucleus in the magnetic field. In the case of free radicals, the G factors slightly deviate from the free spin of 2.0023. Now coming on to the last topic of today's lecture, which is the application and the important topic. Applications are based on 4 properties of the ESR: their intensity, their width, their position, that is the G factor, and the multiplate structure. ESR is a sensitive tool to study the samples containing paramagnetic species. It can be used to study extremely rapid substitution reactions of paramagnetic ions by measuring line width. The line components of ESR provide information about the type of nuclei present in the vicinity of the odd electron. The relative intensity of the ESR line confirms the type of nuclei which are responsible for the hyperfine coupling. And the summation of the intensities can be utilized to evaluate the total number of free electrons. So, based on all these 4 important parameters, we can see the applications. The first is the structure determination. However, ESR do not provide structural information, but it tells the extent of delocalization and the symmetry of the molecules from the set of equivalent nuclei. The second is the study of free radicals. ESR is used to study free radical produced by the chemical reactions and irradiation, even if they are produced in a very low concentration. Third application is the study of unstable paramagnetic species. In many chemical reactions, unstable paramagnetic intermediates are formed. ESR studies provide useful information regarding these species. The fourth application is the study of kinetics of the electron transfer reaction. ESR technique is used to study rate constant of a bimolecular reaction. Example, like rapid electron transfer reaction between naphthalene anion system can be easily studied by the technique. Coming on to the fifth application, it is used in the study of inorganic compounds. ESR studies have been carried out on transition metal compounds, especially first transition series in different valence states. The ESR spectra of coordination compounds can be measured in solutions, powdered, solids, or in single crystal. The technique is rapid in solution state, but the exact results and detailed information are obtained in powdered form, where exact value of G is obtained. The reason for this is because in solution form all possible orientations of the complex ion relative to the magnetic field contribute to the resonance and only approximate G value is obtained. The next application is the study of catalyst. ESR spectrum of chromium alumina catalyst is used for distinguishing valence states. The spectra obtained is on the account of superposition of spectra corresponding to 3 phases. A broad line centered at G is equal to 2 is obtained from clustered chromium 3 positive ions. A low field line due to chromium 3 positive, which is in the isolated form, it arises at about 1600 Gauss, and a sharp singlet at about G is equal to 2, it is obtained due to chromium 5 positive. Next application is in the determination of oxidation state of a metal. Copper second complex, that is D9 system, gives a sharp signal, while copper first complex D10 system gives a much reduced signal. It also has some analytical applications like in the determination of manganese ion. In this case, 6 peaks of manganese ions are obtained in solution. The multiplicity of manganese is 5 by 2. So, according to the formula 2I plus 1, we have 6 peaks. Second, in the analysis of vanadium in petroleum oils. Traces of vanadium in petroleum oils causes corrosion in combustion engine and furnaces and alter the catalytic cracking of the petroleum during processing. So, with the help of ESR technique, we can find out whether vanadium is present in the oil or not. Next, we have analysis of polynuclear hydrocarbons. Polynuclear hydrocarbons like anthracene, perlene, dimethylanthracene and naphthalene can be determined by ESR by first converting them to radical cations and then analyzing the free radicals by the ESR spectroscopy. It also has some biological applications, the sum of which are: first, it is used as a major tool to characterize metalloproteins. It is also used to study the kinetics of reactivity of molybdenum in xanthine oxidase. It also finds use to measure the metal-metal distance between chromium 3+ and manganese 2+ nucleotides for various complexes of glutamate synthetase. Free radicals can be detected in healthy and diseased tissues. ESR imaging on animals is done to study the action of brain, heart, liver and tumor growth. Let us see what are the similarities and differences between NMR and ESR. So, NMR versus ESR. Two different energy states are produced due to the alignment of nuclear magnetic moments relative to the applied field in NMR, and the transition between these two levels takes place on the application of radio frequency. So, this was NMR. In ESR, two different energy states are produced due to the alignment of electron magnetic moments relative to the applied field, and the transition between these two levels takes place by the absorption in the microwave region. The transition in NMR occurs at frequency in the radio frequency region, while in ESR transition occurs in microwave region. The chemical shift phenomena is present in NMR. We have already studied this in the technique NMR, while this phenomena, chemical shift, it is absent in ESR. So, this was all about the technique of ESR. In today's lecture, we have studied the technique ESR, its introduction, its instrumentation, its principle, its application. So, this was the end of the spectroscopic methods. In this whole series on the spectroscopic methods, we have studied many techniques like NMR, ESR, UV visible spectroscopy, IR, flame photometry, atomic absorption spectroscopy, ICP and so on. So, with this we end with this series. Thank you so much. Thank you.